So before we get into structures of complexes, I wanted to go back and talk about electron configuration because I believe there's something that we didn't talk about when we're filling up the d orbitals. I know that this is a topic I discussed in 201, but I'm not quite sure if it was covered this last spring. So um, we talk uh, we talk about filling up these orbitals. If we take something, let me see, let me get the periodic table here. Just want to look at one. There. Um, let's go with just go with potassium. So potassium has 19 electrons. So when we write the electron configuration, and let me see if I can just draw these orbitals out here. So here we have 1s, 2s, 2p, yes, p, 4s, 4p, 4d. So 1s, 2s, 2p. And this isn't according to energy level. I don't have any energy levels up right now. We're just talking about filling up these orbitals, 3p, 4p, 4d. So potassium has 19 electrons. And generally it goes 1s2, 2s2, 2p6, 3s2, P6. And I'm going to stop right there. So we have 2 electrons. So the 1s2, 2s2. Let's get 2p6. 2. All right. So here we have 6, 12, 6, 18. So we've used 18 um, electrons now. So now this last and final electron. Um, when we write the electron configuration is 4s1, right? We completely bypass the 3D and we put that electron into the 4s. So we completely bypass the 3D here. And this applies to when we're filling up the electrons, not when we're taking them out, not when we're making charges, right? We're making charges. I've already shown you how to do that in the last lecture, where we talked about taking them from the highest energy level, right? We take them from the highest energy level, remove them from there, but as we're filling them up, uh, we want to make it so that the orbitals are stable. And orbitals are most stable when they're half full or when they're, I should put or, not of, or full. So when an orbital is half full or completely full, and if we take a look at this, we have a choice of putting the electron, here or here. So if I put this electron here, well, is that half full or completely full? It's neither. It's not very stable in that subshell, right? But here, if I put the electron here, well, that means that it is half full. It's a lot more stable. If we make this calcium and we have to add 2 electrons, well, then we would add another electron, and that would be a full orbital, right? And now that the 4s is done, now we're actually forced. So anything else is actually just forced um, into the orbital after we've completed the subshell there. But part of when we're filling up these electrons is that when we're filling them up, not when we're removing electrons, but we're filling it up, is that we choose it by the orbital best. Do I put it in the 4s or do I put it in the 4d, right? And that's just chosen by making the orbital either half full or completely full. So I just wanted to make sure that we did cover that. And then now we'll continue where we got structures of complexes. So moving right along. So structures of complexes. So structures of complexes are based off of the coordination number, right? We talked about coordination number, and this is the number of ligands that are attached to that central atom. So something, and let me see, let's put coordination number. So anything with a coordination number of 2 is something that we're going to refer to as linear, right? Linear means there's only 2 ligands attached to it. And your book has these examples here, but I'm actually going to draw them out, not just give you the complex. So something like NH3, and there's the 2, right, for coordination. And it would look something like this. So Ag, and then we'd have NH3, NH3, and we could see that that's very linear just by the shape of this here. Coordination number of 3, we're going to have something that we call trigonal planar. So something that's trigonal planar is this is a very flat structure, right? It's a very flat structure. Let's see, how about, so what is this, copper cyanide? We'd have copper in the middle, and then these are all going to be 120 degrees apart, but it is a very flat structure. Let's see, we'll put some cyanide. And you know what, let me look at something here. There's cobalt. I'm just looking, so I want to see if maybe I can show you the structure of this. Cu, something that's very linear. Let me share that. Let me see if I can look this up on my chem. Nice shoes, right? Let's look this up. 3D chem.com. I don't know if it'll show up here, but let's see if it'll load. So library of inorganic structures. Let's look at copper. And something that's very planar, something that's trigonal planar. Do they have anything here? They have something that's tetrahedral. They have something that's very linear. Let's see. What was the first one? Nope, not that one. Ag. So we had gold here. Oh, perfect. Look at that. Right. So we can see something that's very linear. Let's see. Oh, is it sharing? Yep, it is perfect. Right. So we have some. So this is Ag and you can see how linear that is. Let me see if we can find something that's trigonal planar. Don't see anything here. We have CuCl2. There's some with 5 coordination. Let's see if we can find a different molecule. How about cobalt? Cobalt's got tetrahedral. Oh, there we is that CO? Nope, that's CO. Well, I guess that's still trigonal planar. There's an oxygen on there. Oh, how about something like this? There we go. So we're just imagine the central atom. So we can see how this is very flat, right? If we were just to rotate this just a little bit, we'd have something that's very flat. Let me see if it will give me a 3D model of it. Oh, yeah, perfect. Stop spinning for a minute. Yep. And we can see how flat that something that's trigonal planar is, right? Uh, and let's see here. Something with coordination number of 4. So something with a coordination number 4 is going to end up being a tetrahedral. Let's see, how about nickel oxide all around? All right, something that's a tetrahedral here. Let's see if we can find nickel cobalt. Maybe they have the actual one here. Of 12. Yep, there it is. Perfect. Right. So we can see that tetrahedral shape here. Central atom being nickel, and then a carbon monoxide coming off of that. Then we have something, we have a couple of them with a coordination number of 5. So the um, first one being trigonal bipyramidal. So trigonal bipyramidal. Not pyramidal, but we pronounce it pyramidal. So trigonal bipyramidal. Um, and how about what we got? VOCN4. And we have an oxygen coming off, right? 2 coming to the back. Have coming forward. Let's see any all around here. Nope, that's square pyramid. Oh, I'm drawing the wrong structure. Oh, that is for square pyramidal. Wrong structure. Cobalt. I was looking at square pyramidal. Cl5. Still 2 minus. Let's put cobalt in the middle. Still not. There we go. Something like that. Jesus. Probably, you guys are probably getting angry with me right now. Trigonal. Yeah, there we go. I think this. Yeah, the trigonal bipyramidal. It kind of forms 2 3-sided pyramids, right? If we were to kind of take a look at it, so right, so we'd have like something here, uh, here, and So we can see how it just kind of forms maybe a three-sided pyramid here. And let me see if we can come up with some kind of structure here. I'll come back to this page. So cobalt, so COCl5. Let's see if we can find it. COCl4. Oh, that'll form an octahedral. Something with a coordination number of 5. We can take a look at this one. So it's not chlorine, but we can still take a look at something that is trigonal bipyramidal. Let's try looking somewhere like this. Yeah, so something like this here. Um, where the ammonia, right? So we see the ammonia, that's going to be the nitrogen. The ammonia is going to be the blue balls here with the white ones representing hydrogen, and nickel or cobalt being the center one. But we can see that trigonal bipyramidal. So the structure of that looking something like this here. Let's see. Then we have the next one, which is still going to be a coordination number of 5, and this is going to be what we call square planar. So we hear something like that's planar, that these are very flat molecules again, when we hear that term planar. So, oh, no, square pyramidal, where I am jumping ahead. Square pyramidal. And let's see, CN4. So there's an oxygen here, then 4 cyanide around it. Put oxygen. And then we'll put CN all around it. So something like that. I don't know if you guys are drawing it, so let me just give you a second before I try and show you. Does the book not give you square planar? I don't know why the book wouldn't give you something that's square planar. But I don't see them showing you that structure. No, they don't show. Oh, that's a coordination. Oh, I skipped right over it. We'll go back to it, but there is square planar. All right. So square pyramidal. Uh, let's see what we have here. Oh, nope, doesn't look like they have anything with a coordination number of 5 here. Oh, we can use this one here. Yep, perfect. So instead of CN, they're just using chlorine here. But here we'd have something that, and I'll give you guys this website as well, this 3dchem.com. Let me see if I can just give that to you guys. There you go. All right, so we see something. So this is going to be square pyramidal. Square planar is going to look really similar to this, except it's not going to have the molecule. It's either pointing up or down. So square planar is going to be square planar would be a coordination number of 4, and we'll do that one right now. before I forget. So square planar. And we'll use where again we'd have nickel in the middle, and then we'd have two going back. And again, planar would be something that's very flat. So kind of look like the square pyramidal, except we don't have anything going towards the top here. So let's look at something. Looks like they're not using chlorine, they're using cyanide for this one. But we can still look at the structure. So even though the coordination number is 4, it's not a tetrahedral, right? Is that here we see something that's very, very flat. Let it stop spinning. So this is not a tetrahedral, right? You can see that this is very, very flat, even though it does have a coordination number of 4. So something like this would represent square planar, right? If we want to see something that is tetrahedral, right, versus something that's tetrahedral, we can definitely see a different shape where this is not flat, right? It doesn't matter which way I rotate this. Nope, not going to be able to rotate that one. Any other tetrahedral ones? How about this one here? Tetrahedral, and no, nope. SCN5, tetrahedral. Nope. Oh, will not give me one for tetrahedral. Won't let me rotate it. All right, well, let's go back. Then we have a couple. No, we just have one for the. We're gonna we're just gonna stop at 6. We can keep continuing on coordination number 7, 8, 9, 10, 12, but we're just gonna stop at 6. So something that's 6 represent an octahedral. So something like what do we have here? Just cobalt again. Where we'd have our central atom, 2 going back, 2 coming forward, fluorine all around, right? And represented. So let's look up cobalt chloride here. Do they have? Oh, we have something with coordination number 6, but not. So coordination number 6. So this is another. This does still represent an octahedral, but it's just going to be a different octahedral. How about one with water all around? Let me see if I can position this correctly. So something similar to what I've drawn. We have the 2 going forward, and then we have 2 in the back, 2 in the front, uh, right? 2 going away from you, 2 coming towards you. We have 1 going straight up, 1 going straight down, and this would represent an octahedral. All right. the chlorine two going away from you, two coming towards you. It's why we use the darkened wedges, and then we go one up, one down. So if you've never seen these, I'm hoping that you've seen these. Like if we write a darkened wedge like or a dashed wedge like uh, this means that that molecule is going away from you. And if we use a darkened wedge, that means that it's coming towards you. It's used a lot more in organic chemistry, but we should have been introduced to those in 201. But if not, that's what those dashes and wedges mean there, just to kind of give some 3D dimension into a two-dimensional drawing to give a little bit better understanding. So looking at octahedrals, continue with just some octahedrals. If we change some of these ligands around, um, and let's see here. So let me just draw a basic structure here. So this is just kind of a basic structure of an octahedral. I'm just going to draw my bonds in without anything else. So an octahedral is going to look something like that. So if we put a chlorine up here and a chlorine down here, and then let's put water on the other ones. All right, is that when we look at this, is that this actually represents a trans configuration, right? And what's trans is these chlorines, right? As trans meaning, opposite, right, on the complete other end. So these here, right, that there's a 180-degree difference between this chlorine and this chlorine, right? They're 180 degrees opposite of each other. Then if I were to draw another structure here, um, but how about we move one of the chlorines and we'll put one of the chlorines here instead. So the angle here between both of these is about, it's 90-ish degrees, right? And that this is something we would call cis, right? So we can have cis and trans in these coordination complexes, right? And let's take a look at one where it's actually, maybe we can see a better configuration of this trans here. Do they have anything here? Let's take a look. Nation number of 6. We'll look at trans. We'll look at those two in just a minute. I don't want to bring those two up yet. I do see some here that are one here that's trans. We might have to wait until we get a different. COCl2. Let's try a different molecule. How about we'll go with let's look at iron here. There's some octahedrals. No, I don't see. So we'll just have to wait till we get. There's some other structures that are more complex, and you'll be able to see the cis and trans in those. I already have them pre-selected here. All right. So let's make it with a more complex ligand here. So we talked about this ligand here. En, right? So let's make this complex here. We'll put cobalt in the middle. Structures. Basic structure for an octahedral is going to look like this. So we'll put Cl here, we'll put Cl here, and then we'll put En. So En is that NH2. So NH2 would look, it would, and this is the En right here. This the NH2. So if we remember, En is equal to NH2, CH2, CH2, and NH2, right? So that's our En, and we can see that here where I've drawn it. NH2, here's CH2, another CH2, and then bonded to NH2, right? So here we also have trans, right? Is that we're looking at chlorine, and chlorine here between these two, right, is that we can see that those are trans. But those aren't the only ones that are trans, right? Is that this is also trans to each other. Those are 180 degrees in the opposite direction. So those are also trans. As far as cis goes with that, so let's draw something that's cis. I always just, when I'm drawing these out, I always just start out with a basic octahedral structure because I can put the ligands anywhere that I feel like. So here, let's make that chlorine cis kind of like we did up here, right? So we made those 90 degrees there by putting those together that closely. And then I'm going to put NH2 along the rest of it. And we'll just join those together with two carbons, join these together with two carbons. And now we have them as cis, right? So not only, but again, we run into these two are now cis, but as well, these two are also now cis. And the cis ones, these cis ones can actually, what we have, we get are what we call optical isomers, right? Optical isomers is that if I were to draw its mirror image here, Cl, Cl. So now I'm just drawing its mirror image. So here's this mirror image. These two are going to connect over here, and these two will connect over here. And again, they're both cis, but these now represent optical isomers. So they represent optical isomers, and optical isomers are non-superimposable. So we'll write that down is that they are non-superimposable. So you can't place one. So they are different, right? Even though they look the same, they are different. You couldn't stack one on top of the other, right? Can't put your left hand on top of your right hand and have them look exactly the same, right? Um, but they also affect polarized light, right? Is that they also affect polarized light. So optical isomers can bend light, twist it, right? So we talk about plane polarized light. So plane polarized light we can just imagine maybe this circle right here, right? And here's a slit here. And plane polarized light's very, very vertical. Wasn't very, let me see if I could draw it a little bit straighter. There we go, right? And when we talk about optical isomers can turn it clockwise. We'd get what we call a positive rotation going this direction, but it can also go this counterclockwise direction, right? Uh, would consider that negative, but this is the effect of isomers, right? When we have an even mixture, we call it racemic. When we have an even mixture, um, if the solution was 50% one isomer, 50% the other isomer, we'd have a racemic mixture and we get something like this here, right? But if we're completely with one of these cis configurations, either 100% the one on the left, 100% the one on the right, is that we would twist that light and have it, going into either clockwise or counterclockwise direction there. So now we can kind of talk about, that brings us to what we're going to call crystal field theory. So we're going to get an introduction into crystal field theory. For those of you that keep advancing in chemistry, you talk about this a lot more in inorganic chemistry, even physical chemistry. Um, so we're just going to kind of get our feet wet here and talk about crystal field theory, right? So crystal field theory. So this involves unhybridized d orbitals of the central atom, right? Unhybridized. So you've already talked about unhybridized p orbitals, right? The s and p orbitals, where you hybridize those for like CH3, CH2, CH. That we're now going to kind of consider the unhybridized d orbitals. So we'll write that down. So this involves the unhybridized d orbitals of the central atom. And it allows us to understand the structure, the color, uh, and the magnetic behavior of these complexes, right? So we'll write that down now. So it allows us, let me see, it allows us to understand structure, color, and magnetic behavior. Right. So our d orbitals here, I'm going to try and draw these out. I know there's a photo in the book, but I think I'd rather just kind of draw these out here. So we're going to go with these. So our three axes, z, y, and our x axis here. So here and here. So this will represent our z-axis, and this will represent the y-axis, and this will represent our x-axis. And then we'll put our orbitals here. So our d orbitals, we're going to look something on like this here, little figure 8 pattern. And then over here along this axis. Right. And this is actually represented. So this is going to represent something we call the dx squared sub x squared y squared. Uh, but these orbitals can definitely take a different direction, right? Uh, let's draw this one here. take a little bit longer. Let's see. This one's kind of so it's kind of got an odd shape here. And it has like this little. It's an orbital here, but it kind of just looks like a little donut. All right. So that's another d orbital. This is what we call the dxy sub xy orbital. Then we have a few more to draw. Let me draw the other ones down a little bit lower here. So the orbitals can take a different direction, right? Is that they can, right? And again, this is our z-axis here. So one will be going upwards, right? In this up-down direction. And then another one can be along the x-axis. Right, so we can change the direction here so that that one orbital's going directly up, and this would be called what we call the dxz, right? Dxz here. I think I labeled one of these wrong. The diz. Nope, z squared. There we go. There we go. This is the dz squared. There we go. Mislabeled that one. All right, so then we have another direction here. How about going up? So we can still have this one pointing up. But now let's have it go along the y-axis, this other orbital here. Right. So this was the first one was dxz, right? And now this would be the dyz, or dyz. And then I think our last one over here, as actually goes in between them. It lays flat. It's going to look like this one over here, but they're not along the axis, as they're in between the axis. So let me see if I can get that drawn here. The one will be along, so in between the axes here. And then the other one is not going up or down, right? Is that it's going to kind of look like this. Um, Gonna be laying flat here. So that one's kind of laying flat, similar to this one here. So this is laying on the actual in between the axis on a very horizontal area there. And then this one would be represented. This is our dxy. So there we have these five orbitals, right? Five orbitals in this d subshell here. Um, And if we take a look at these here, these actually have some, I drew them out this way specifically because these represent something we're going to call the T2g orbitals. The T2g orbitals. The T2g orbitals, these orbitals point between ligands. The T2g orbitals point between ligands, and these down here are known as the EG. Let me write a sub G. EG orbitals, right? Um, and the EG orbitals, these actually point towards the ligands. So we have two that point away from the ligands, and then we have some that point uh, towards the ligands. D2G, and I think you know what? Don't hate me. EG, T2G. There we go. EG, T2G. I know that because T represents triple, and we can see that there's 3 there. So the triple is what, and when we say triple, they're triple in degenerate energy level. So I'll be using that. I think I'll use that term degenerate. Degenerate simply means that those orbitals are in the same energy level, right? So we have triple degenerate orbitals here in the same energy level. So for an exam, that's how you'll remember that T for triple, and it's going to be these specific orbitals. So in an octahedral, so in an octahedral complex, the EG orbitals are what we call destabilized. When they're destabilized, they're in a higher energy level. So this is my energy level. So in an octahedral complex, we'll write that down, is the EG orbitals are destabilized, meaning that they are just in a higher energy, or just higher in energy, right? So the EG orbitals are higher in energy, right? And our T2g orbitals would then be lower in energy, right? And our T2 orbitals are going to be degenerate. They're in the same energy level. So here, let me put it in black here, right? This would be our EG, and this would be our T2g. And the difference here, the change, so we're going to use this symbol here, right? That symbol here, this represents something that we call crystal field splitting. And this one in particular is crystal field splitting of an octahedral, right? I could change that and I could put like tetra there, and that'd be the crystal field splitting of that tetrahedral. So what is crystal field splitting, right? Crystal field splitting is the difference in energy level there, right? That we definitely have different energy levels for these, right? So this is my dz squared, this is my dx squared y squared, then we have dxy, dxz, dyz, right? So the crystal field splitting is the difference in the energy levels of those EG orbitals and then those T2g orbitals. So this here, right, the crystal field splitting is dependent on, so it depends on the metal charge. It depends on the ligand. It also depends on the orbitals, right? So we'll talk about the ligands first here before we do the metal charge. We'll talk about orbitals. So we'll talk about the ligands here. So we have two different types of ligands, right? We have what's called weak field ligands, and we also have what we call strong field ligands. A weak field ligand is going to have a small splitting, right? Or let's just write this here. It's going to have a small splitting, right? This is crystal field splitting, right? Remember, that's what that means. This little symbol here means that we have field splitting, right? So weak field ligands have a small splitting, and strong field ligands have a, oh, come on, a large splitting, right? Or they have a large splitting, right? It means the same thing. Large splitting, large delta OCT, right? It means the same thing. So as far as ligands go, we do have, I'm not going to give you every single ligand, right? But I will give you ligands that we're going to maybe see on the exam or maybe see in your homework. So a ligand can be simply just a halogen, right? We can see halogens. So this would be kind of, and we'll go in this direction here. We'll go in increasing field strength, right? So iodine is the weakest, then we get Br minus, and then we get Cl minus, and then we get F minus. Then some neutral ones, we got water here. We got C2. This is another ligand here. Ammonia. N minus, and I think we'll stop at cyanide. And there are more, but that's a pretty comprehensive list. So we're going to stop. This is going to be our break point here, right? Where we're going to consider these to be weak and these to be strong, right? So weak field ligands here, strong field ligands here. And that'll kind of be our break point. Right, so we're talking about splitting, right? If we talk about splitting, I just pick a couple here. We'll say that Cl minus would have a smaller splitting. So Cl minus would have a smaller splitting, and I'll even put it down here. a smaller, right? Smaller delta OCT, right? Smaller delta octahedral splitting there, versus, let's say, NO2, right? Is that weak field ligand versus strong field ligand, small splitting, large splitting. So why does this splitting even matter, right? Why does this splitting even matter? Well, it matters when we start filling up the d orbital, right? Is we have to go with, right? So remember our d orbital, right? Our d orbital here, and we go with what we call the, you might remember the term aft-bow, off-bow. Remember this off-bow principle? This is how we fill up these orbitals. Well, electrons will singly occupy degenerate orbitals before pairing, right? So according to this off-bow principle, electrons will singly occupy degenerate, and again, degenerate meaning the same energy level, right? So we'll occupy degenerate orbitals, so orbitals in the same energy level, before pairing. And the weak field, strong field ligands really help decide these, how we occupy and fill up these orbitals. So when electrons pair, the energy they use is called pairing energy, right? The energy is called a horrible S. It's a horrible G. And I should give you guys all like Starbucks cards for having to read my having to read my writing here. So it's called pairing energy, or capital P here, right? So when electrons pair in an orbital, that is called pairing energy. And the magnitude of that splitting and the energy pairing determine which orbitals will be occupied. Why does it say, what does it say before occupy and singly? So let me read. I'm going to read off this first one over here. So electrons will singly occupy degenerate orbitals before pairing. Does that help, Emmy?
Yes, thank you.
Got it. Starbucks card is in the mail. All right. So the magnitude. So let's say the magnitude of the splitting and the pairing energy determine which orbitals will be occupied. Which ones will be occupied? So let's take a look at a couple of complexes here. So let's use iron. Iron, making an octahedral, so Cn, this is 6. All right. So Cn, right? Let's draw our energy here. Nope. Energy. Spread these out a little more. All right. So Cn, right? This is a strong field ligand. And how do I know it's strong? Because I'm going to go to this list over here and look where cyanide is over there. So it's one of the strong field ligands, which means it's going to have a large splitting. So I have to put some distance between the T2g and the EG. So let's go ahead and put it up. Let me really give it some distance here so we can really tell. Oop. So I'm going to adjust these a little bit so I can really give it some distance here. Right. Strong field ligand, I'm going to have a pretty large splitting, right? For a um, strong field ligand. So strong field ligand, this is a large splitting. So I put some distance between those. So here we have our EG up here, and then this will be down our T2G down here. But because of this splitting here, right? Iron in the d orbital, we're just looking at the d orbital. Iron has 6 electrons in that d orbital. So in order to fill up these orbitals here, we have to take in consideration this large splitting that I'm going to put some electrons in here. 1, 2, 3. Now I know that we told you before when you're doing electron configuration, right? We fill up the orbitals, 1 electron in each one, and then we decide, well, you know what? This is how we really do it, right? So we're now pretty advanced in Gen Chem, and we're deciding where to put these electrons. It takes a lot of energy. The larger this splitting is, the harder it is to get an electron up here. So because it's a strong field ligand, and because the energy or the large splitting here, this is what we're going to consider a low spin complex. And we're going to fill up here, here, and here. So all of these electrons are going to stay in the T2g because of this large splitting. There's not enough energy to throw and excite one of those electrons up into those EG orbitals, right? It's just that the splitting is too far. So this is what we call low spin complex. A low spin complex. And what comes from a low spin complex is that it minimizes unpaired electrons. So a complex with a strong field ligand will minimize unpaired electrons. Here we see that we have 0 unpaired electrons, 0 unpaired, and we have 3 paired, right? So 0 unpaired, 3 pairs of electrons. I should put 3 paired. I should put pairs, not paired about that. 3 pairs of electrons. Well, now let's look at something with a weak field ligand. So weak field ligand, how about we use water? Water's a weak field ligand. And how do I know that it's weak? Well, let's take a look at our list here. You see that breakpoint that I gave you? Oh, where'd it go? There it is, right? Weak field ligand, water would be considered a weak field ligand. So weak field ligand contain a small splitting, right? Weak field ligands contain a small splitting. So let's take a look there. So I'm going to draw my energy out. Here's my energy. I'm going to start with my T2g. And because I have a small splitting, right, this is now, right, now I have a small splitting because of water here. This is a weak field ligand. Weak field ligand equals small splitting. So now that there's not much difference in energy between the EG and the T2G, this is what we're going to consider this a high spin complex. Because now these electrons can go into there. So if I got 6 electrons, high spin, meaning that we're going to be able to get those electrons into the EG because there's a small splitting difference here. And what happens to that is, look what happens. This does not minimize, high spin complexes don't minimize the number of unpaired electrons. I need 6 electrons, so I think I left one out here. So what happens with this this high spin complex? Well, let's see. We have one pair of electrons, and then we have 4 unpaired electrons. All right, one pair and then 4 unpaired electrons. Okay? So that's kind of our what happens with these weak field ligands, these strong field ligands, is that there is a difference, and we definitely fill up these d orbitals differently depending on the strength of that ligand. Uh, tetrahedral. Tetrahedral has a different shape to the orbitals. So we're talking about a tetrahedral. You know what? Let me label this up here. We should label this octahedral. 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 And this is going to be a tetrahedral. So our tetrahedral um, looks like this. So this is what our tetrahedral. And to confuse the T2G and the EG, we simply just call this T, and this is going to be E, right? So we see here, and instead of delta OCT, I'm going to put delta, like delta tetra, right? And that'll be our splitting here. So this again, this will represent T, and this will represent E, not T2G, but just T, and then this will represent E. And it just so happens that for tetrahedrals, and I'm going to put this on here, all tetrahedrals. Big enough, love you. All tetrahedrals are small splitting. So all tetrahedrals are small, right? That they're all going to be high spin, right? That they're all high spin for a tetrahedral. Uh, and they get more complex. I mean, we could have one. So I think like square planar. Square planar is really an odd one here. So square planar is really going to look something like this. Yeah, square planar will look something like this, where too high. Go down to this one here, where this would be EG and this would be T2g here, and they get, but I think this is a little more advanced than I want to get. This still represents an octahedral, but this would be for like square planar. But as far as the exam goes, I think we're just going to stick with tetrahedral or octahedral. We're not going to. I'm not going to put anything there that has square planar, because then our EG and our T2g orbitals get changed up a bit. So we'll just stick with the tetrahedral and the octahedral ones. So we talked about ligands, right? And now we can talk about what we call magnetic moments. So magnetic moments in molecules and ions. So magnetic moments, we have these terms, what we call paramagnetic and diamagnetic, right? Paramagnetic molecules, paramagnetic ions are attracted to magnetic fields. While diamagnetic, these are not attracted to magnetic fields. Right. So paramagnetic molecules, ions, or complexes are attracted to magnetic fields. Diamagnetic, not attracted to magnetic fields. They're actually repelled, right? Uh, Paramagnetic. This is where we find unpaired electrons. This is where we find unpaired electrons, and here there are no unpaired electrons. Is that they are all paired up. All paired up. Probably going to go. I need about another 10 minutes, so we'll probably go. Yeah, we might be able to finish this. So I did want to show you guys a video on paramagnetism. It'll take just a couple minutes here, but let me go ahead and share this video. I've shown it to my 201 students. You guys might remember it. So you were in my 201 class. There we go. Put it full screen. Can you guys see the full screen there? I don't know. Can't even see my chat. Okay, all right, good. Can you guys hear it?
Not really. No.
No, not at all?
No.
No, all right. So what she's holding nitrogen, liquid nitrogen, and in here there is a magnetic field. So she's going to pour the liquid nitrogen, which is diamagnetic, right? And it's actually going to be repelled. And oxygen is magnetic, right? And to prove that, the guy there, he's going to pour in liquid oxygen, and you're going to see the difference here. So she has um, nitrogen, liquid nitrogen, which is diamagnetic. Let me, here she is. So this is, right, it's being repelled. The nitrogen is diamagnetic. And he's now going to put in liquid oxygen. So oxygen is magnetic. Oxygen has unpaired electrons. And you can see that, right? So it is magnetic. Oxygen does have or will be affected by a magnetic field. And it'll do that until it finally all boils off. All right. And now we kind of get to color. So we've talked about structure, we've talked about ligands, and now we'll actually talk about color. So I'm going to draw this out. This is just a color wheel. Um, we'll start out with, what is this, 400, and we'll go to 480, 620. And these are all in nanometers. Nanometers, or we have red over here, put blue down here. Let's see, we got yellow over here. I'm gonna run out of colors. That's all right. Put orange over here, and about purple. Put purple. All right, so green. Let me just blue, and then we have purple there. All right. So we're gonna have to recall a couple of formulas, right? We're gonna have to recall Planck's equation, where we have frequency. So frequency is equal to the speed of light over wavelength, right? This represents speed of light. Jog that memory. We'll use 3.00 times 10 to the 8th meters per second. And this represents wavelengths. Wavelengths in meters. And this represents frequency, right? That little fancy V frequency, which is either going to be in per second. Um, I'll put not slash, I'll put or. Hertz, right? I'm out of paper here, so let me. So that's one formula that we do need to recall. And then we need to remember this, right? Energy is equal to, right? This being Planck's constant. Planck's constant, which is, what is it, 6.63 times 10 to the negative 34 joule seconds. Joule seconds, right? I'll put an arrow there, right? So that's Planck's constant. And again, we already decided, right, that this was frequency. So, right, frequency there. So, uh, if we have the wavelength, so if we put any of these complexes, and we can determine the wavelength of them. If we know the wavelength there, we can determine the frequency, we can determine the energy, and the energy we're actually going to calculate is the splitting, is that we can calculate the splitting energy of these complexes. Right, so that's what's going to help us calculate that. So let's do one calculation here. How about we use copper? Now, this complex absorbs light. Let's see, it absorbs, we'll say red-orange. This absorbs red, orange light. It absorbs red, orange light. So let's determine from this color wheel here, red, orange light is, you know, I think it's right there. It's about, 620 nanometers. So we've already figured out our wavelength, and we can put that into Planck's equation. So if we know what light absorbs, and I would tell you what light it absorbs, I would tell you. So it absorbs red, orange light. If I had said it absorbs, let's say I said it absorbed yellow light, right? We could say that's about 570 nanometers. If I said purple, well, that'd be about 415 nanometers, right? So here, the red, orange, I'm going to guesstimate that to be about 620 nanometers. So that's going to be, that's my kind of my starting point, 600 nanometers. So in order to calculate the splitting, you need to calculate frequency, right? Calculate frequency, and then we're going to calculate energy, right? Calculate frequency, calculate energy. Well, let's use Planck's constant. So frequency is equal to the speed of light, 3.00, times 10 to the 8th meters per second over the wavelength in meters. So I have 620 nanometers. I'm going to multiply that by, let's see, for every 1 nanometer, I have 10 to the minus 9 meters. So can somebody calculate this out? I didn't do the calculation. Cancel our units, so this cancels, meters canceled, and I am left with per second, which is hertz. Got my frequency. Should be a relatively large number. Anybody? Anybody?
If I did this correctly, I got 4.84 times 10 to the negative 4.
10 to the -4.
Mm-hmm.
It should be a relatively large number.
I got to the -14.
To the -14.
I mean, to the times 10 to 14.
Okay, that sounds more like, yep, that sounds more like it.
Oh, yeah. Mm-hmm.
So 10 to the 14. Okay, so now we have frequency. So now we can use Planck's constant. So this is the formula I'm using now. I'm using this formula here, and I'm going to use Planck's constant, 6.63 times 10 to the -34, 6.63 times 10 to the -34 joule seconds times 4.84 times 10 to the 14 per second, or hertz. Those units will cancel out, and I'm left with energy in joules. So the energy is equal to what? This is probably going to be a really small number. Should be negative something. Negative 19-ish.
I got 2.68 times 10 to the -19.
Everybody good with that? Anybody else get that? And I did just verify that. If you did not get this, I just verified it. If you did not get this value, we need to figure out the there's some issue there if you're getting negative. Negative 19. Yeah, that sounds good. Yep. 3.2. So let's just have Elisa recalculate that.
I'm
As
still like
I
15.
just got 3.2 as well.
I get 2.67. Is that just like rounding or?
No, I got 6.63 times 10 to the -34 times 4.84 times 10 to the 14 is I get 3.2.
Oh, that's an 8.
Yes,
Oh, I
8.
put a 0.
Oh, gotcha. There we go. Yep. So 3.2
Yep.
times 10 to the -19. And this would just be in joules. So that is our answer here. So that is our splitting there. So with that finishes off chapter 19, actually.